We'll use inclusion-exclusion for another example, in this case counting a certain type of function. Just as a reminder before I get into the definition, if we have a function that's defined from a set, let's say A with elements A1 through AM, to a set B with elements B1 through Bn, N for narwhal, I think we said, then we can specify or depict that function by saying for each input, what are the outputs? These over here are the potential outputs. They don't have to all be used. So let's go ahead and sketch one out here. So a function might do something like the following. For A1, we have to make a choice, and maybe we make the choice B2 as the output. For A2, we have to make a choice. Maybe we'll make Bn as the output. But the point is that for each input, and there are m of them, we have n choices for an output. So we have n choices at each step, and there are m steps. So the total number of functions is n to the m, where n represents the size of the codomain or potential output set, and the exponent represents how many elements there are in the domain, how many times we have to make that choice, and n is how many choices we have each step. An onto function is one that uses every one of the potential outputs as an output. It is onto a function from a set A to B maps onto B if for every B in the codomain, the potential output set, there is an A that has B as that output. There is an A such that f of A is equal to B. That's an onto function. It covers B, uses all the elements of B. And the theorem we want to pursue talks about the number of functions from a set A with m elements onto, and I needed to correct that and make a correct that typo, onto a set B with n elements. The way we'll do this is by taking the total that we have above here, n to the m, and subtracting from it the number that are not onto, our good old complement thinking here as well. And so I've started the next line, but I haven't put the final answer there. So we're going to analyze what's in the brackets first of all. This part right here, we're going to analyze that by looking individually at the number of functions that miss one of the output, potential outputs at a time, and then two, and so forth. So for each I, the set that miss output bi, say bi is up here, and we're going to miss that as an output. Nothing uses it, and maybe there are other ones missed too, but ai will be those, all of them that miss bi. Then what has to happen here is that we still have m steps to define the function, m for monkey, but each time we only have n minus 1 choices because bi is no longer a choice up here. bi is no longer a choice. So we have n minus 1 to the m, and if we add all of those up, there are m for monkey different ways that we, n for narwhal, different ways we can miss. N different ones we can miss up here above. There are n different ones we can miss. So there's n, choose one that we're going to miss, and then n minus 1 to the m ways that can be missed in a function. And then for two of them, A intersect A, J, if we have two particular ones, then there are n minus 2 choices at each step that we are considering the output for an input from AM. M of those choices, m of those steps, that is to say, each step there are n minus 2 possible values in B that we can use as an output because we've disallowed I and J. And if we sum all of those values, the sizes of those, then there are n choose 2 ways to decide which ones will not be output values in the range, and at each step for each of the input m inputs we have n minus 2 choices. And this continues on in that fashion so that the numbers not onto let me do the last one. So the last one would look like A1 intersect A2 intersect out to AN, but omit one of them, like J, because it makes no sense to talk about a function to B that misses every possible output value. It has to have at least one, and the least it can have is 1, in which case it's a constant function. So these really are the constant functions, and so in this case here Bj would be the constant output value, because we're told it misses every other one but Bj. And so how many of those are there? Well, it's one possible output every time, and the sum of those would be how many ways we can pick n minus 1 to miss, leaving 1 that we use as a constant function times 1 to the m, which of course is just 1. Right? So that's what it is there. I didn't want to write out all these sets in here. Crazy to write them all out. That's the idea. So the total things in the bracket that we have above, I'm talking about this bracket here, what I mean by that is this one here, this bracket here would be equal to n, choose 1, n minus 1 to the m. Those are the sum of the sizes of the sets individually, and then using inclusion exclusion minus the next grouping, the sum of those where we take the intersection of 2 at a time, n choose 2, n minus 2 to the m. So the n choose 2 is counting how many of them there are. That gives us the sum. And then plus, minus, dot, dot, dot. And notice the parity here. When we had an even here, we have a minus sign. So there's the minus 1 power is raised to a power that is 1 different than this number here. So I'll write that as n minus 2, 1 different. And then we have 1 to the m there. So that's what we're subtracting, and so I'm going to go ahead and do that, subtract that above, and I'll go back to the blue here and see that what we have there is minus this first term, n choose 1, n minus 1 to the m, plus it will now be, because I'm the subtraction above, plus n choose 2, I'll get rid of that now, n minus 2 to the m. So the m power is staying constant in here, and then it will be minus plus all the way to the n, and it's minus 1 now to the n minus 1 power. N, choose n minus 1, which is just n, I know, and then 1 to the m. So I'll write it in its full glory there. That's our theorem right there. So let's do a very quick example. Let's take, for example, the number of functions from a set A equal to, say, 1, 2, 3, 4 are its elements, onto B equal to the set whose elements are A, B, C, just 3. And so in this case here we have M is equal to 4 and N is equal to 3. And so using the expression above, we would have 3 to the 4th for the first term, minus 3 choose 1, and then we have 2 to the 4th, and then we have plus 3 choose 2, and then we have 1 to the 4th, and that's the clue that we stop when we hit 1 there. Okay, that's the clue to stop. And you can add those up and see that what you get out of that is 36.